Hello, I'd like to go ahead and do a talk on what I'm calling the human brain function above all other and the creation model. And hopefully by the time that I've gone through this material, you'll have a better sense of what I'm trying to refer to. So first of all, thinking about brain function, and I'm going to be focusing that in terms of a human that is above all other types of creation, all other brains that are operating. And then I'm going to introduce the creation model as a way of getting a little bit more insight. Let me go ahead and use a couple slides here to do an introduction, and hopefully this will fill in some of the details. The human brain functions at a level beyond any other brain among all animals. Since human beings are made in the image of God, or Imago Dei, there must be signatures of this fact in the design. So in this talk, we'll introduce an engineering methodology for exploring this concept. In terms of scope, what we're going to talk about here, which will focus on brain exploration as a key neurological building block, neurons and networks of them. What I'll do in the future, but beyond the scope of what this discussion is going to be here, we'll get into more details. So an architectural model of the neurons and neural networks in the human brain, the central nervous system, and the human body is developed. Additionally, a creation model is constructed. Utilizing these models, it offers the potential to unpack human Imago Dei reality. This premise provides a rich area to explore that leverages the biblical creation to capture the engineering framework God used in fashioning creation and his crowning achievement, human beings. By including the design and purpose of man from a biblical point of view, the most significant engineering context for human brain processing can be captured. A computer science full compute stack model will map neuron and neural functions to the various computing layers. To adequately include human capability, it is shown that an extra full compute stack layer is required. So I know there's a lot of different things that were going to be discussed here: theology, biology, computer science, neuroscience, and neuromorphic computing. So hopefully if you just stay with me, you'll get a better chance of what we're going to be covering. Well, let's start to think about what are the research questions that we'll be thinking about here. So the resulting insights from its inclusions is discussed, the inclusion of all these different topics. So in this talk will analyze brain neurons and neural networks using system engineering methods and the system modeling language to capture an architectural drivers that are the main things that we want to be focusing on. The aim is to provide new insights and guide future work. Two complementary modeling points of view are included: neuroscience, where biological neurons and neural network details are captured at a top level, and two, neuromorphic computing, where the artificial implementation approaches of neuron and neural networks are highlighted. And then in terms of the research questions, thinking from these two different points of view, the answers to three research questions are discussed. One, how does the creation model provide additional insights and context for the implementation and mission of human beings? Two, what modifications to the full compute stack model are required to capture unique human brain function? And three, what observations about human brain function can be made from the neuron and neural network architectural models? So hopefully you'll see how that works here. Based on those three research questions, we're going to take them one at a time and talk about the information related to that. So first, let's talk about the creation architectural model. So we're going to be using something that I call the reverse engineering object-oriented systems engineering method, or REOSM. And so these are the 6 steps that I've outlined of how what is required to make this work. And this is something that I've talked about in other papers, so I'm not going to go into that in too much detail, but I'm going to show you some architectural products that give you a sense of how this all fits. So real briefly though, first of all, you survey the the academic literature, textbooks for information on the biology. So this is trying to focus on how we look at biological systems. Then you want to be capturing this information in descriptive information of this is how typically what is done in the biological exploration, you describe things. But when you want to be engineering things, you have to put it into prescriptive information, having things that are called requirements. The system shall do X, Y, Z. Then you want to start to be capturing that into an architecture. And then as you develop that architecture, you get more and more specific. So first you start with high-level functional architecture. And a tool that I'm going to be using is something called SysML, which is a it can do system architectural modeling, and that's what I'm going to be doing there. And finally, you can be doing an evaluation of the architecture. Well, the neat thing about what we're talking about here for thinking about the creation model is we're going to be using the biblical text. And so basically, let's go to Genesis 1 and start to get an insight of what the creation week looks like from a engineering perspective. So the creation model will allow for comparison in the same engineering terms, creation features, and what human brain functions can be understood from the neuron and the neural network models used in this discussion. Thus, brain function and the environment it was created to function within are drawn together. It allows the first research question to be answered. That is, how does a creation model provide additional insights and context for the implementation and mission of human beings? Genesis 1 provides a roadmap for how creation took place. One, consider what was created each day and the order. There is an interrelationship between the parts of the creation week. As the detail of the creation week unfolds, the latter items utilize what has already been conceived. Thus, there is an intentional plan that is laid out. This section will discuss the creation week element and present the details within a system engineering model, the SysML engine with the SysML tool. And so that's what I'm showing here. I'm showing you a model of what we're trying to do, capture the information in Genesis 1 for creation. First, consider the overall flow of creation. That's where a good place for us to start. I would imagine some of you have noticed the structure of the flow of how things are laid out in Genesis 1. And it is pretty interesting to see how that works. And as a result of the next handful of slides, I'm going to try and give you a perspective, maybe from a point of view that you haven't thought about. So each day forms a part of creation, so they all feed into the block on the left. And so that's what I'm trying to show here, the way that I've oriented this block definition diagram, as it's called. Day 1 starts with a creation with space, time, and light and matter. These basic building blocks must be in place before anything else can continue. Day 2 forms the Earth's expanse, creating an atmosphere and space where life can exist above the terrestrial water and below the atmospheric moisture. Day 3 makes the lands, oceans, and vegetations, thus several ecosystems are put in place. Day 4 establishes the space expanse. So we have two different expanses that are laid out here. The sun, moon, and stars are correctly oriented with the Earth. Day 5 sets the beginning of the eukaryotic life and the animals of the sea and the birds in the air. Finally, day 6 continues the creation week by forming animal life on land. Ultimately, the crowning portion of the creation week concludes with the creation of humanity. Humans are made in the image of God and given his divine charter to reign over creation. Note that the number of items listed in the daily creation events varies. The days with fewer items indicates they deserve a day all to themselves. Another interesting perspective. So after this overall look at creation week, it is helpful to go down to the next level of detail since it is included in the creation week account. So let's go ahead and now just unpack this one day at a time. So day one starts with the formation of space and time. This fact is not stated, but it is implied in the Genesis 1:1 phrase referring to the creation of the heavens and the earth. There can be no heavens and no earth without space and time. So there are two items laid out first. Continuing to the next item, there is electromagnetic radiation or light. This requires space and time and the heavens and the earth to have an effect. Light interacts with matter, so in the process of making the heavens and the earth, the material matter of the heavens and the earth is formed. Next, there is a distinction between there is a electromagnetic energy present, light, and when there is no electromagnetic energy present, that is darkness. More characteristics of electromagnetic energy are implied, thus like the occulting of light when a mass is in front of an electromagnetic energy. Hence, the necessary features for an eclipse are present. This leads to the final part of day one creation, where there is the potential to have day and night. Since time is operational now, the clock has started and a 24-day is now in place for an observer on Earth, although an atmosphere, land, and life have not yet been introduced. Moving on to day two creation focuses on the habitability of Earth and the basis of the Earth's expanse that exists with the numerous properties required to support abundant biological life. First, it is implied that water was created on day one and it can manipulate where it is located. An atmosphere is generated. Second, water is moved to subterranean locations that can be called upon to support plant and animal life. Third, some water is transformed into water vapor and it resides in the upper atmosphere, acting as a shield for the Earth's expanse. Water is transparent in the human visual spectrum, so seeing the space expanse is still available. So the nominal environment is that you can see, even though there is some water vapor, that you can still see the heavens. Moving on to day three sees several features introduced that are crucial elements to sustain life. First, there are distinctive characteristics of land and ocean conceived. The ground will have direct access to the atmosphere. The sea can draw nutrients from the atmospheric in different ways while in the water. Second, there is a separation of the land and ocean. At this point, there is a predictable place for land and sea. To each domain's animal and plant life can be adapted to its special intended environment. Third, there is a general creation of vegetation over the earth. Fourth, there is the first mention of vegetation, which includes providing food for others. Fifth, there are various kinds of seed-bearing vegetation, including grains. So there is another type of food source and a reproductive method for vegetation to reproduce with seeds. So that finishes the first triplet that we have in terms of the creation model that we can see here, as I was showing on this slide. And let's now get into the second triplet. So day four focuses on the space expanse. So we have the Earth expanse and then the space expanse. Day four focuses on the space expanse. And first, the sun, moon, and stars are placed within the space expanse. Second, the properties of the electromagnetic radiation matter or leveraged to enable the day to be light, and the electromagnetic energy coming from the sun and the darkness of night with no direct access to the light of the sun. Third, specific orbital relationships are set up between the Earth, the Moon, and the solar system and the Milky Way galaxy. This allows for the signs of the days, the months, the seasons, and the years when there is completion of the regular cycles that the Earth travels through over time. Fourth, the sun governs the light and brightness of the day. The light and warmth of the sun promote life. Fifth, the reflected light from the sun on the moon governs the brightness of the night. for the times that the moon is visible at a particular location on the Earth. So that's day 4, day 5. Day 5 begins the process of creating animal life. The description is short, but focuses on the two significant biospheres of Earth. First, the oceans are populated with animals after their kind, and second, the air is filled with birds with their kind. Before the land was filled with life, the oceans and skies above were called forth to teem with living creatures. And then finally, we have the very important day 6 that covers two significant areas in populating land. First, God created the land animals after their kind. Second, God spends more detail focusing on the crowning portion of creation, describing the details of creating man in the image of God. Two things are explained. Unlike any other part of creation, man is uniquely created in God's image, enabling him to be creative and think at an abstract level that no other part of creation can. Then man is given a mission to rule over creation and to be God's representative. So just to finish up here, so we can be answering some information about this first question. Since God created the heavens and the earth, God, the engineer, had a master plan for his implementation. With human beings made last as the crowning part of creation, there are many ways and many levels in which they engage with those resources. The creation model translates the creation narrative into an engineering format that is much easier to use for design evaluation. With this model and what is developed by the full compute stack model discussed next, there can be a comparison of some aspects of human beings in terms of the environment in which they were created to prosper within. Human beings indeed engage with the physical and biological world like other animals. Still, the capabilities they possess go far beyond basic living functions. With the resources available, individuals can create, design, and engineer many things that can improve their ability to fill their Imago Dei charter. Human beings transcend beyond just existing. They can leverage the physical and biological order laid out in creation to think in some ways as God does. They can create from the resources God has provided. And so what I'm trying to show in this slide here goes beyond to what I've just mentioned. There's also this dialogue with the Holy Spirit that I think is important, that we want to be mindful. So that's the first of 3 parts with the research questions that I wanted to address. Now I want to get into the second part. This is where I get into what's called the full compute stack model. And so this is something that's used in computer science to look at neuromorphic computing, to look at computational models. And so that's where it came from. And I'm applying it here to be looking at the brain. And there is some literature that shows this. So 7 layers are used to convey the full compute stack model. And the literature shows that it has been applied to neuromorphic computing, a discipline seeking to emulate brain-like capability. By considering the limitations of what can be captured with this model, is quickly apparent that another layer is required to capture human-level function. Although generative artificial intelligence shows a higher level interaction of the elements in the full compute stack, it still does not have the ability to capture all human-level function. And so basically what I'm postulating is there needs to be an extra layer laid out, and I'll give some level of introduction to what that might look like. So this is just another way of looking at those levels. And so let me just go into some more thoughts on this. That the full compute stack model provides a manner to explore brain function. It lays out a scaffolding for the layers that go from simple to complex. Utilizing the full stack model with brain function creates a basis to determine whether the model is adequate to cover human brain function or just animal brain function. Thus, it allows us to address a second research question: what modifications to the full compute stack model required to capture unique brain functions that are found in humans? An architectural framework bounds a project and provides a structure to organize major thrusts in a system. This will be utilized in what we're going to talk about here. An existing architectural framework will be utilized to structure areas of exploration in neuron and neuronal system evaluation, which is the focus of what we're trying to do in this talk. The layers of the full compute stack are used as a framework to capture the multi-layered functional operations of neural systems. The full compute stack is a layered abstraction of what a computing capability can offer and fits well with the purposes of this project. The layers are the material layers, the components and device layers, that's number 2, 3, circuits, 4, microarchitecture, 5, system architecture, 6, algorithms, and 7, algorithms. And so basically what you're finding is there's a growing in complexity, but an interconnectedness between each of these layers. And in a couple of charts, I'll get into a little bit more detail to give you another perspective of how that would look like. I'll look at a use case diagram and an activity diagram to hopefully give you a better sense of how those are related. This is a resource that I was leveraging when I did some of my research, and it was trying to consider what would it take to do the neuromorphic computing realization of a human brain. And so this is a quote from this resource here. In terms of power utilization, the human brain is exceedingly energy efficient in specific tasks. By comparison, to simulate a brain composed of 100 trillion synapses and consumes 20 watts of power, 96 supercomputers are required utilizing 16 gigawatts of power. So getting these kind of resources is a far cry away from what would be necessary to do that equivalent to what we would find in the human brain. So it really falls short. And I would argue still there's this other layer that is not actually adequately dealt with. So I'm going to be focusing on 4 categories of brain activities with the next couple of slides that will give you some insight into this. So we'll be talking about sensing. A good example would be looking at the eye, and there's been a lot of neuroscience research that has been focusing on that. Motor control, how we can see the relationship between what we're able to touch or engage all of the muscles and everything to have fine motor control. 3 is learning. We have the ability to take information and then integrate that and improve upon how we actually engage on one activity or not, whether it's learning how to speak a language or something else. And finally, the computing, to be able to analyze and think through complex types of things that are one of the key areas that's unique for the human brain. So this bottom diagram is fairly simple, but this is partly what I'm trying to do is I'm trying to have simple diagrams that starts to convey what we are able to accomplish. And so here we're using this full compute stack model and relating it to human function. So considering the biological neuron and neural network linkage of the full stack layers, what we're showing here is a use case relationship between the layers, and the next figure will show the type of activities and linkages between the layers. Many independent elements must function together to accomplish the desired computing and processing goals. Although many details are presented, it is still notional, trying to capture how a use case scenario for critical application connects to all the lower levels in the full compute stack. So this is just a simple relationship that each level within this full stack computer connects can go up or down one level. And that's what I'm trying to show with this type of a model. Well, this is a more complicated diagram, and I will highlight some things in just a minute, but each of these layers are shown here in these yellow rectangles. And then we have different types of activities or that are contained in each one of these layers, starting with the materials layer, working into the device and component layers, having those things then go into circuits, having that fit into architectures. And this is complicated enough that there's two levels of architectures that are discussed. And then the things that would be more familiar to what we would like to be using is thinking about an algorithm and a certain approach for doing things. And then finally, an application, which is the highest level of functionality that is captured in the full compute stack model. So thinking back to this chart about these four different things that we're accomplishing, what I want to then is just to highlight what I tried to do with this activity diagram was to highlight here in these mid to upper level of the full compute stack is where we can get some differentiation between these four different types of categories of mental functioning that we can do: motor control, sensing, brain computation, and learning. So this is really just a high level look at this, but what we can see that there still is something that is not captured here. To go to this level of abstract thinking, you can have a pre-recorded response with some of the things that AI is starting to capture, but it really doesn't have this kind of an engagement here. And so I'm going to focus a little bit of our time as we finish up this section to talk about this. So an additional layer is proposed to account for the human brain's unique characteristics adequately. This attempts to account for human beings made in the image of God and the fact that man has a body and soul that intersects in the physical world, but includes a transcendent element that extends beyond the realm of the spirit. It is essential to consider how mankind transcends the mental capability of being of any other created organism. Being made in God's image, human brain functions must consider the spiritual dimension. Neurons and neural network descriptions do not adequately cover this dimension. So one of the references that I have in my paper, Schaefer notes that just realizing a neural network does not mean that learning will occur all on its own. And there's a companion paper that's associated with that for those folks that want to look that up. No human level emergent properties are manifested by just building neural network hardware. So this is what Schaefer points out. Schaefer may be giving evidence for brain activity that engages with non-physical input. Humans must be animated with the spirit to be alive in the sense that God intended for humanity. Leveraging theological knowledge, conceiving abductive arguments that capture how human consciousness is more than neural networks is straightforward. Although not explained in current neuroscience research, knowing that man is created in the image of God, there must be interfaces such as between the human brain, biology, and the soul, along with the soul to spirit if considered separately, and two, between the spirit and God. This is a possible extrapolation from what Schaefer is pointing out when he argues that there is no free lunch. Can't just create a neural network and voila, things just start to happen. Creating elaborate neural networks is not enough to capture what is required to make it possible for this type of learning that can only be done in the human brain. Only neural networks with external interfacing capabilities allows the abstract thinking and the ability to capture the full design of human consciousness. And so this is what I'm trying to do. Once again, these architectural diagrams are meant to be as simple as possible to convey the point. And so basically we have the Holy Spirit, and one of the things that you can annotate here is this term called stakeholder, is engaging in the life of a human being. They can engage the body. And so there's that domain, and there's also engage in the things that are unique to humans at this higher level way of able to think both spiritually and cognitively at a level that other creation cannot do. All right, so just to finish up here, what is the question here for the second part? What modifications to the full compute stack model are required to capture unique brain functions? And so without modifications, our Imago Dei faculties cannot be captured with a full compute stack model. Human brain function, above all other, shows a clear differentiation from animals with the human spirit and the manifold engagements that occur with the Holy Spirit. The full compute stack model targets general computational purposes and has been demonstrated to capture capability layers in neuromorphic computing. It does not allow for distinguishing the differences between an animal and human beings. With the additional insight given in scripture about human nature, it might be possible to pursue a generative artificial intelligence inspired approach that assumes every part of the human faculties can be mapped exclusively into a physicalist implementation understanding of functions. But really, this contradicts the level of agency that is captured in the Imago Dei Charter humanity has been given. Thus, there must be modification to the model to allow for a higher level faculty that includes abstract thinking and the human spirit that animates the human body. And so that's what I conclude for this second research question that I'm trying to address in this talk. Third, let's think about the neuron and the neural network model. And so you might recall that I showed this reverse engineering object-oriented system engineering method, or REOSM, when I was trying to create a creation model in engineering terms. And so the bulk of what this paper and this talk are focusing on really is this area, but I wanted to put this in a larger context. And due to time limitations, I'm only going to be able to give an overview, but I follow these 6 steps again. And let me just quickly go over the types of things that I did in terms of capturing some information in the neuroscience research to translate into engineering terms. So there were a variety of things that were looked at. So we have the neuron models, classification and architectures. We have the neural circuits and response experiments, spiking neural networks, and neuromorphic computing were all of the 4 major research threats. And so 2 were focused in the neuroscience area, and 2 were focusing on the neuromorphic computing side. And so there is an interesting interrelationship between those 2 that I'm trying to capture. So basically, my point is that there's a 2-front approach. There's a neuroscience approach, and there's a neuromorphic computing approach. And so what I have been trying to do with this research and what I'm capturing in this talk is to bring those 2 together and hopefully point out how this can be helpful to give insight that otherwise would not be available. So this section is focusing on neurons and neural networks. And so let's start here by describing what is a neuron. A neuron is a specialized cell that receives, processes, and transmits nerve impulses. In a learning model, it develops connections with other neurons to collaborate in computational efforts as needed. From a computing point of view, a neuron can be considered a computational device that consists of a processing unit, memory, and inputs and output devices. In contrast to a centralized von Neumann architecture, and so I put this in here. This isn't part of the block definition diagram, but it's trying to highlight these 3 major things. So in contrast to a centralized von Neumann computing architecture with separate processing, memory, and input and output modules, each neuron is a self-contained computing agent that can be networked with other neurons to form networks. How a neuron implements each of the three von Neumann architecture elements is explained next to clarify what is meant by comparing an individual neuron with a computational element. So there's a textbook that I use when I teach computer architecture. It's written by Stallings, and so it is a very good reference for what you can be doing in electronic computer organization and architecture, but I'm not going to get into that. So neurons process and condition the information it receives. This processing level is lower than one would associate with a laptop's central processing unit, or CPU. However, looking at a CPU, it is at its architecture, one can find a better level of processing comparison. A relatively recent innovation in processor implementation has multi-processor cores. Thus, with multiple cores, a CPU shares duties with multiple processing elements and assigns duties to each based on how it is engineered. A key workhorse within the CPU is something called the arithmetic logic unit. And so that is something that is within a processor core. The arithmetic logic unit is a device that can be commanded and configured to perform various computational operations. This is done by software with a low-level programming language called assembly language. A more appropriate analogy exists with an individual neuron at more targeted arithmetic logic unit level. A network of neurons could be considered similar to a multi-core processor. Thus, a single neuron can be considered an arithmetic logic unit with a handful of programmable and reconfigurable states. In one of these states, a single neuron is configured to do some basic functions like sum three inputs, pass the input if a condition is met, amplify the input, or modify the input in a particular fashion. So there's a number of references in the paper that goes along with this that I won't go into. So that's the first thing. I talk about the central processing unit and have it at a lower level where there starts to be a viable comparison between that and what you would find in a neuron. Second, there is the memory, so focus on that. There is a memory in a neuron. Each neuron must maintain awareness of what it must do at a given moment. Through learning activities, a neuron can respond to a stimulus in the same way repeatedly. Networks of neurons require memory to execute multi-stage activities. Each action requires memory and various, and there are references that I've referred to in my paper that explore aspects of neuroscience research concerning neurons and neural network memory. Third, and finally, there's the input and outputs. Neurons have the capabilities for input and outputs, as demonstrated by studies examining and visualizing neural network structures. Computational load can be shared by having neurons work together in the appropriate input-output connections. The central nervous system connects neurons to pass sensor information and monitor motor functions. Neural circuits have been experimentally traced, and so there's some references that I've shown with the literature review that I include. So that was a mouthful, but just to summarize here, I'm trying to show a neuron as a building block for something larger, which we see in neural networks, which is a big piece of what takes place in brain function. So there are multiple ways one can characterize the classification of neurons. One can consider the functions and the structure. So those are going to be the two main things that I'm going to talk about here. So what I'm showing in this figure are two classification categories that are used in the assessment. Since the neurons are a key focus for the paper and for this talk, that the section provides useful characteristics for the basic building block. Showcasing information via an architectural model perspective highlights the taxonomy and implementation information in biological neurons and what approaches are done in biomimicry that are used in artificial neurons. Neural network models are shown in a later slide, and so we'll get to that shortly. And spiking neural networks are implemented in biological networks. Artificial neural networks models are simplifying attempts to implement some of the features in biological spiking neural networks within the current limitation of electronic chip part fabrication methods. Functional and structural classifications are highlighted. Functional classifications capture the capabilities that are at the top level of biological neuron types by location, and structural classifications summarize the major biological neuron implementation types. So first, let's talk about the functional classifications. So they capture the significant types of neurons and their locations. The location of the neuron relates to their functions. These functional locations are near the sensor, near the senses. So those would be sensory neurons, as I'm showing in the figure. Inside the brain, that would be interneurons. So we'll see that here. Inside the central nervous system, which would be interneurons. And finally, the near muscles, what are the motor neurons? So neuroscience research seeks to refine the understanding, but from an architectural modeling point of view, these classifications are enough to provide a top-level understanding of sensing, motor function, computing, and learning. Remember, that was what I was talking about when I was using the full compute stack model to be thinking about this. So neuron functional classification highlights what neurons are intended to do in the architectural layout used to embrace its purpose. Does not fit directly one-to-one into a von Neumann architecture of a processor, memory, input, and output. Still, it does show all three of these von Neumann features. There is not a clear distinction between hardware and software. Digital computing is not necessarily its base, but spikes are used to trigger actions and pass information. A different architectural paradigm is utilized for this important connecting and computational building block. It is optimized to promote interconnections, share computational loads, learn from the past events, process sensor data, and do motor functions. All these can be boiled down to the worker, thinking of like a honeybee as an example, to think like a worker bee perspective. So you break things down into a lower level, and they all work together. Honeybees work together, ants work together, just to build on that analogy. So describing the next layer of specification, neurons can be grouped into four functions: sensor neurons that interface with the senses, interneurons in the brain that focuses on computation and learning, interneurons in the central nervous system that focus on connecting and signal processing of the information being transported, and motor neurons that focus on motor control. To accomplish many activities requires two or more of these functional neuron categories to work together. Note that none of these functions capture the unique qualities found in human beings or the special qualities that are part of the human's Imago Dei charter. So that's the first thing, talking about a functional classification. Now let's think about the structural classification. So these capture the number of connections a type of neuron has. So thus we're thinking in terms of structure. The three classes are unipolar, pseudo-unipolar, bipolar, and multipolar. A unipolar neuron has a single dendrite. A bipolar neuron has one dendrite and one axon. Multipolar neurons are typical in the nervous system and have long axons. This type of architectural classification approach groups neurons by their physiology. neuroscience research is actively working to characterize neurons when they can be exposed in their operational mode. In contrast to functional descriptions, the structural taxonomy highlights the observable features accessible by physical observations. Biological neuron structures take advantage of the three-dimensional space where they exist to make connections. That's really pretty novel when you think about it. Electronics can't do that. Each structural classification does the same basic function of transferring information through the organism, with each also doing signal conditioning or computational processing of the information. Unipolar neurons exist in invertebrates like insects, but not in humans. They are part of gland and muscular functions. Pseudo unipolar neurons exist as sensory neurons. Their primary function is to route sensor data back to the brain for processing. Bipolar neurons represent the classical structure of a neuron in one input node via the dendrite and one output node with the axon and synapses. Multipolar neurons are the most common type of neurons and are heavily populated in the central nervous system. This diversity in structural options for the neuron shows how flexible its general capability can be utilized to serve many functions. Okay, so we talked about the functional and structural characteristics of a neuron, and in this talk we're focusing on the neuron, and now we're going to be talking about a few other aspects of the neuron way that is designed. So neuron synapse signaling is the next thing. So several steps occur when information is sent from one neuron to the other. The axon prepares information for proper transmission to the synapse. Then the neurotransmitter takes that processed information and makes it ready to leave the synapse and transition the physical bond from the transmitting neuron to the receiving neuron. Next, the receiving neuron takes in the information and the transmission is complete. This figure shows the neuron synapse signaling process. So we have the transmitting neuron, we have the receiving neuron, and this is the way that is captured, and the literature review is where I got that and tried to do an architectural model to be thinking about that. Well, we have one of these four different types of neurons that I'm focusing on, and this is trying to be thinking about the sensory neuron. Since sensory input is a comprehensive function done with a collection of neurons, it is important to characterize the relationships between the components that are part of this activity. And so this figure shows us. And so here we have the input from the sensor. So the sensor goes directly to the neuron, and the neuron then is going to be passing this on to other neurons in the central nervous system, where it's then going to go to the brain to be processed. And so this is mostly a one-way function that we have. And so we have a sensory input, the dendrite excitation, say there's multiple sensory inputs, and so we have all of those connected. You have the neural processing, the conditioning of the signal, and then the propagation of the results are all captured in that model. Okay, with the full compute stack, I did mention that there were two layers of a architecture. The first one was a microarchitecture, and so this is trying to be showing what that microarchitecture is like. From a neuromorphic computing point of view, there are hardware implementations that try to be creating this type of a structure. And so this is actually based on a block diagram from Intel with two chips that they have designed with this relatively straightforward process, but it's still adequately capturing the architecture of the microarchitecture of a network of neurons or a neural network. So you have the inputs, that you have a learning feedback loop that is taking place, And so this is still focusing this in terms of more or less of a neuron point of view with this type of a neural network microarchitectural model. Okay, now just to be finishing up, for artificial neural network models, these are the types of things that are out there. And so since most neurons are deep within the brain, it is tough to access experimentally uncover the functions of the neuron. So this figure tries to show two types of neural network models. An artificial neural network is much easier to implement depending on the model used. It can range from a modest to average realization of what occurs in a neural network. And one of the main things that is talked about based on the neuroscience research is that there's a spiking phenomenology that is seen in neural networks. And so it's like it turns on and off. It's just a periodic way of information that is passed from neuron to neuron. And then when they're not activated, they go into a low power mode. So this is really how things are done in the biological realm. In the artificial neural networks, then we have these levels of models that try and figure out how far they're going to go in terms of replicating that spiking neural network type of capability. And so I'm not going to go into these details, but these are examples of three models that are out there in the artificial neural network world that is trying to create neural networks that have some of the capability that is on this side, but it is a far cry from what actually is out there. I'll finish up in the next slide, but I decided to include this just to give you an idea of what is on the biology side in green. What are the components that's shown in black, and what's done in the artificial world in the electronic or perspective of how they would go about building a neuron and building neural networks. And so you have an artificial neural network down here versus a brain neural network where you have one neuron connecting to another, and they're trying to mimic what this processing is for each neuron as inputs are aggregated together in a neural network. So I'm not going to go into this in detail, but I did make an argument about a von Neumann architecture. And so we have memory, processing, and we have inputs and outputs. All of these are represented in this figure. So let's finish up with this research question, the third one. And so what observations about human brain function can be made from neural and neural network architecture models? So what I'm trying to be doing with this discussion is trying to manage complexity with architectural models, try and make things that are more accessible. And so relatively speaking, hopefully the diagrams that you were seeing were more or less easier to comprehend. And you were seeing the soundtrack that I was giving got into more details. But hopefully if we start with a top level way of conceiving this, it makes it more manageable. And that's what the goal is, what I'm trying to do. So what observations can we make about human brain function from the neuron and neural network architectural models? So much work has been done in both neuroscience and neuromorphic computing. With so many basic features in neuroscience that still are unknown, capturing architecture models can provide a framework for how to view this complex information. Since the biological neuron implementation details are complex and not wholly characterized, an architectural modeling offers a different approach to identify design methods and interdependencies. Neurons are a fundamental building block in every part of human neural systems. In general, they accomplish the same function using a common basic architecture. There is a specialized tuned functionality when moving towards more individualized neuron types as one compares capabilities like sensing, motor control, computing, and learning. And so we talked about some things getting into more details like the functional classification. One way of showing functional neuron classification is to bin neuron types into sensor, interneuron, motor neurons, and those are the three main things that we have. And then I talked about some of the sub classifications for that. There are two types of interneurons, one in the central nervous system and one in the brain. Even at this high level view, there is a tree structure where all neurons have a variety of common characteristics. Still, then there are additional specialized features that are utilized for specific missions. Sensor neurons cooperatively work with the sensors. Motor neurons are tailored to work with muscles and ensure proper control. Interneurons focus on relaying information and doing a portion of the computational load. The central nervous system is primarily a transport mechanism, while the brain neurons take relayed information and perform computation and learning functions. So that's for function. And then for structural neuron classification focus on physical implementation differences and how they vary from one neuron class to the other. Major structural differences group neurons into unipolar, bipolar, and multipolar. A unipolar neuron has a single dendrite, a bipolar neuron has one dendrite and one axon, which is useful for direct and indirect cell pathways like in the eyes. Multipolar neurons are typically in the nervous systems and have long axons. This type of architectural classification of grouping neurons by their physiology. So that's a synopsis of what I wanted to capture there. So let's just finish up with 2 slides and try and bring these 3 research questions together. Human beings being designed with mental capabilities that exceed all other animals. They were created to live in harmony within the creation fashioned for them on Earth. Utilizing the full stack model, the capabilities of humans go beyond what its layers can capture. With the focus on neurons and neural networks in this talk, it is possible to capture how the Imago Dei translates to this level with an architectural model. Much about neurons and neural networks still need to be uncovered, creating an architectural context along with what is already determined with neuroscience research and the challenges that have occurred with neuromorphic computing. Trying to implement comparable system gives insight into how much capability is packed into the human brain. It is asserted that generative artificial intelligence will never match what humans can do. There are missing architectural layers that cannot be included in artificial systems. Humans' responses can be codified and aspects of learning can be captured in machine learning approaches. Still, this does not mean that artificial systems will have the breath of life from God given to them, as we see in Genesis 2. So just to finish, above all other parts of creation, the human brain alone can think and process abstract ideas. Humankind should be the last part of creation, since they are interdependencies between man and every other aspect of God's handiwork. More importantly, humankind is called to rule and reign over creation and held accountable to be a good steward. Individuals report directly to God and carry the bidding of our sovereign God to the ends of the earth. Neurons are a fundamental building block to the various parts of computational tasks. Biological neurons are a complex and adaptable building block used in many human and animal physiological places. Several categories and types within each category exist. This is a very active area within neuroscience. Artificial neurons and neural networks are not able to meet the capability and the modest resources necessary that are found in their biological counterparts. Neural networks are collections of neurons that form cooperative structures that allow them to operate together through learning and optimization from repetitive tasks. exploring neural networks and computation in general in terms of a full compute stack. The full compute stack layers is a helpful way to capture the levels of functional capabilities that must cooperate to bring together a working computational capability. Specific engineering choices are seen in the implementations of these layers. Research continues to provide new insights into how these functions work. Although this talk, along with the paper, integrates various ideas for framing and understanding of neurons and neural networks, the work requires more development because there is a limited understanding of neuron and neural network biology, and artificial implementations are rapidly changing. Continuing to track the developments in neuroscience, machine learning, and neuromorphic computing will be required. And so there's plans to have follow-on survey papers and that can be going into more specific research questions. And so that is something that will be done in the future. From the biblical creation model, there is evident interdependence between each creation layer. As the temporal plan of creation unfolds, the latter, more developed layers depend on the infrastructure from the earlier temporal created steps. Once all creation is functional, each aspect has a tightly coupled and finely tuned partnership. Humankind is part of this system, but is also unique in its ability to understand and explore its operational makeup. Similarly, the human brain is the most advanced brain that can be considered with the architectural model layers to see a similar interdependence among all the layers. This layered engineering design pattern with interdependence and fine-tuning is seen in many aspects of biological life. An additional layer is proposed to account for the human brain's unique characteristic adequately. From an architectural point of view, this accounts for human beings made in the image of God and the fact that man has a body and soul that intersects in the physical world, but includes a transcendent element that extends beyond the realm of the spirit. Using the creation model, the assets of the full compute stack, and the architectural models of neuron and neural networks it shows a shortfall between human brain function and what artificial neuromorphic computing systems can achieve. Using the context seen with the creation model, the purposes of creation becomes clear from an engineering sense. Creation is about relationships and drawing all aspects of creation into greater intimacy with God. This is far different from simply increasing neuromorphic computational capability. All right, well, thank you very much.